hardest ACT math questions. When explaining things, it can get a little bit tedious and time-consuming. And this is the aftermath of about 20 minutes of me trying to explain this first problem. And I realized I probably should try to make it through a couple more, and at a quicker pace than 20 minutes per problem. So, with that in mind, I won't delve as deep into the explanations. So, this first question here has an equation and a graph that corresponds with it. It says the equation is h equals a times t squared plus b times t plus c. And this describes the height of a baseball over a certain amount of time. And it's kind of misleading in the sense that it looks like it actually looks like a three-dimensional sketch of what a baseball is doing, and you picture it, this being the height, which it is here, but you kind of picture this being the distance, the horizontal distance, when it's really just the time. So you want to keep that in mind when we're trying to solve these and think through what the question's asking us. So it says, if you alter only this equation's c term, which gives the height at time 0, the alteration has an effect on which of the following? So I'll go through these one at a time. The h-intercept. And for this one, all you really need to know is that h-intercept is in fact the height at time equals 0. So it kind of gives you that one. And that just means that when t over here is 0, what height are you starting at? What height does this equation tell you the ball should be at? And it's this spot right here. So, next. So our answer would be, it does in fact have an effect on the h-intercept when we alter the c term. So it is number 1. So we can eliminate GH right off the bat. Now number 2, the maximum value of y, of h. So here we'll reference my little doodle. And I drew this, and I think I took about 10 minutes to explain that the maximum height is entirely relative to the initial height. So whatever the height is initially, the ball will go up until its velocity upward. As I said, as I tried to write here, v equals 0 at the zenith, I suppose you might say. Sorry, I had some company there for a second. I forgot I was around explaining the, I guess, correlation between the initial height oh, that's it, the velocity. The ball initially has a horizontal and vertical velocity, and gravity works in a downward force. That's what these arrows are here. So it doesn't actually affect the horizontal velocity of the ball. So the horizontal velocity will stay relatively constant, minus air drag and effects like that. But the vertical velocity will be some initial position, value I mean, and will incrementally decrease until it hits the height at which its velocity is 0, because gravity is in fact trying to pull it downwards, and that has the effect of decreasing the velocity to 0, and then ultimately making it reverse direction right at this point at which it goes down to the ground. So all that's to say that, yes, if we change the C term from 3, I just used that as an example, to 0 down here, the maximum height will not be the same. And in fact, the ball will hit the ground a lot sooner. I suppose you could think of it as you're already starting with, some amount of height underneath it, and once it hits its peak, it'll have the distance, vertical distance traveled, plus all that initial height underneath it, whereas if it starts at 0, it only has the distance traveled vertically underneath it. So yes, it indeed affects the maximum value of h, and now that narrows it down to only j and k. So basically is the third characteristic affected, the t-intercept. And I guess this explanation shows that the t-intercept would be the point at which not only does it return back to its initial position, but if not 0, it has to go beyond that initial position and hit the ground. Or basically, I guess the t-intercept would be the point at which the height intercepts or intersects the t axis here. So we will think of it as when the height goes to 0, because that's where the t-axis is. So yeah, if we change the c, it will in fact change the value of the time at which the ball ends up at a value of 0. So our answer here would be K. It satisfies all three of those conditions. It affects all of them. Alright, we made it without taking 30 minutes, but still took a lot longer than I wanted to. Try to move at a faster, yet relaxing clip. Alright, so number 2 here. So we have a question for all real numbers b and c, a little word problem here, that such that the product of c and 3 is b. Which of the following expressions represents the sum of c and 3 in terms of b? Alright, so all we have to do here is break this problem into components. We have real numbers, so b, c equal real numbers, meaning they're not imaginary or irrational. Let's see, rational. I might be wrong about that, but we know they're not imaginary, and we have a product. The product of c and 3 is b. So we have c times 3, and that equals b. Which of the following expression represents the sum of c and 3 in terms of b? So we want to know what c plus 3 is, but we don't want to use the variable c. We want to use only numbers and b. So here you would take this equation and solve for c. And then once we know what c equals for this equation, we can simply substitute that into that variable right here. And c should just equal b divided by 3. And then this becomes b. That becomes b divided by 3 plus 3. Alright, so let's look back at our options here. We'll just go ahead and fold this over. And we have b plus 3. No. 3b plus 3. Let's see. What can we do? So this is the expression we have here, and we can manipulate it. If I multiplied let's see. We look at this, and looks like we have a similar answer. So it's E. E would be our solution there. Alright, the next problem we got is for all x in the domain of the function. Let's see here. Let's see, we got x plus 1 divided by x cubed minus x. It says for all x in the domain of that function, this function is equivalent to, and whenever it says that, you can kind of ignore that, because it just means x can't be 0. But when you're solving it in terms of itself, or you're just manipulating the variables, you really don't need to apply that, I don't think. So basically this one just comes down to which of these can we manipulate this into. The top one is already simplified, but when we have a cube and two of the same variables, what you can try to do is pull out an x, pull out one of those variables, and you're left with, so I pulled out an x, and I have x squared minus 1 now. Does that look like something we have? I see x squared minus 1. That's good, but we can't simplify the rest of it to 1. So what I want to do is I see they're looking to see if we remember the difference of squares trick. And this one is particularly tricky because it's hard to forget that 1 is in fact a square of itself. In fact, it's a cube of itself, and it's actually any root, any exponent of itself. And I guess I just mean that you can multiply it by itself as many times as you need, and you'll still get 1. So the difference of squares is where we take this and it's like when you try to, what's the word? Yeah, what's that word? I forget it. I don't know, you try to simplify a quadratic function into something times something else, and you get so basically the rule of difference of squares is if you have a square minus another square, or in other words a difference of two squares, this can decompose into the roots plus each other and the roots minus each other, and you have x plus 1 and x minus 1. And then we can test that by showing you that x times x, so we distribute x to x, and then -1, we get x squared. X squared minus x, and then we distribute that 1 and we get 1 times x is x, 1 times -1 is -1. And negative x plus x is 0. And we are in fact left with x squared plus 1, or minus 1, sorry. So that's all to say that this can be broken up into that. And then we have back to our original function. The original function says x plus 1 divided by x times this, which we just broke up into these two functions. So we have x plus 1 and minus 1. And right away your brain should go back into basic training with algebra equations and realize you can sniff out that this equals 1. So it's like saying 1 times 1 over x times x minus 1, where this one is this thing divided by itself. So anything divided by itself is always 1. So we basically just pull this out and we're left with this. And I would bet that we can find that on our little sheet here. 1 and looks like it's probably this one. If we just go ahead and distribute that x. So x times x is x squared, and x times negative 1 is negative x. And it looks like those two do indeed match up. So, alright. I think we got time for one more. So we have another word problem. For a project in home economics class, Kirk is making a tablecloth for a circular table 3 feet in diameter. So let's just go ahead and draw a circle here. And the diameter d equals 3 feet. Now the finished tablecloth needs to hang down 5 inches over the edge of the table all the way around. So I would immediately draw a bigger circle and 5 inches would be, I don't know, extra. We'll call that 5. So x equals 5 inches. So I guess we'll use the little tick marks there. And to finish the edge of the tablecloth, Kirk will fold under and sew down 1 inch of the material all around the edge. Kirk is going to use a single piece of rectangular fabric. That is 60 inches wide. What is the shortest length of fabric in inches Kirk could use to make the tablecloth without putting any separate pieces of fabric together? And this one's kind of tricky. let's see, what is this about folding under and sewing down 1 inch of the material all around the edge? Is that included in the 5 inches, or is that another inch all around, making it 6 inches? Should I increase that to 6? What do I do? What would that be? Kirk will fold under this, sew down 1 inch. Yeah, I'm going to say that it's included in the 5 inches. No, sorry, I think I misinterpreted that, because it needs to hang over 5 inches, but that's after he apparently finishes the edge with that extra 1 inch of material. So yeah, I guess X really is 6 inches after all. See, that was kind of tricky. At least that's how I would interpret it. So now if he has a rectangular piece of fabric. It is 60 inches wide, or what is that, 5 feet? 5 feet. And what is the shortest length? Yeah, basically you want to be able to inscribe a circle in there like that, and you want the circle to be 3 feet plus 6 feet all around, or 6 inches all around, which is adding 6 inches to each side, which is a total of 4 feet. So how many, and it wants to know the answer in inches, so we have 48 inches, so we need 48 inches that wide. So yeah, I would say it's 48 inches. Let me see, I got the answers over here. The question is this one, number 4. Okay, yeah, it is 48 inches. That has got to be the trickiest question wording I've ever come across. I really hope they don't actually put that on ACT tests. That's ridiculous. Because they give you what they call is a width, and it's a rectangle, so you assume that if they're giving you the width, you assume that the length that they're looking for is naturally longer. But I suppose a square is just a special case of a rectangle, but I don't know. I don't really. I think that's some. And then the 1 inch thing, that's like, if that was someone delegating a task to a person, this would probably go down in the history books as the most retarded explanation of what you are looking for ever. I think that's pretty ridiculous. Alright, looks like we got some trigonometry next time, so